Hey, good afternoon, everyone. Welcome back to IWQC20. I hope you had an enjoyable morning of quantum chemistry this morning. Our next session is going to begin with our final invited talk of the workshop, which is from Margaret Martonosi, who is a professor of computer science at Princeton University and also is involved in the United States National Science Foundation. So she's going to be talking to us about directions and research perspectives for quantum computing. Margaret, the floor is yours.
Great. Thanks very much. Good morning, good afternoon, good evening, everyone. It's great to be here. As Ross mentioned, I have a unique double affiliation right now. So I'm on the faculty at Princeton University, where I have been since 1994. And then in addition, in the US, scientists go and do rotations at our National Science Foundation, where I'm currently leading the Computer and Information Science and Engineering Directorate. And so this talk is going to be from both of those perspectives. First, as a classical computer scientist, a classical computer architect who's gone into the quantum space and is thinking about architectures and compilers for quantum. And second, from the perspective of the funding agency that funds 85% of the US computer science research and a strong fraction of our math, our physics, our engineering research, and so forth, the perspectives of what are the funding opportunities that we're making available to help advance this field. So with my double hat on, I will start. Emphasis in my research part of the talk on the computer systems part of the puzzle, the part that I've worked on more closely. So I use this very sketchy graph as a visualization to help motivate what I see as opportunities in the field. And so what you can see here on the x-axis is years, and on the y-axis is a log scale, roughly depicting the number of qubits that are either needed or available. And this yellow line is, again, a very rough estimate of where we've been in terms of the number of qubits that are buildable in hardware today. And the blue up here that you see depict the years in which two well-known algorithms in quantum were proposed and a rough estimate of their qubit requirements. And I don't want to sort of dig into the details of the qubit numbers specifically, but I think what we can all agree on is the degree to which there's a gap between these algorithms that the general public knows best about quantum and the kinds of systems we can build right now. But there's some hope on the hardware side. This yellow line that I drew kind of arbitrarily to some degree, we don't know exactly what its slope will look like going forward, kind of like when Gordon Moore drew Moore's law based on just a couple data points in the 1960s. We've noted that the slope has changed over time in Moore's law, and likewise, the slope here could change as well. Clearly, systems builders are getting better at building systems with both more qubit counts and more quantum volume. They're improving qubit coherence time. And there's a general improvement in the level of hardware expertise and systems expertise that we have around building these quantum systems. In addition, another thing to note is the degree to which algorithms have progressed. And so this version of the graph now has things like quantum chemistry, QAOA, new breeds of quantum algorithms that don't offer exponential speedup necessarily, but that offer the chance to get a lot of good practice at lower qubit needs. And many feel they might be potentially the first true examples of usable quantum advantage. And obviously, there are hundreds of quantum algorithms in the quantum zoo to go beyond kind of the general public's view of sort of Shor's being the main one that people know about. So here we are. There's still a large gap, but maybe it's closing. Clearly, what we're in right now has been deemed the NISQ era, large enough to support experiments, too small for the quantum algorithms with known exponential speedup, too small for ECC thus far. But maybe we're getting close to being able to bring some of the other algorithms onto these machines. And in particular, we see, from my perspective as a computer architect, as a compiler person, I see huge opportunities here to bring these two trends together to close the gap sooner. So the more we can advance algorithms and hardware and systems together, the sooner we get this crossover point where the gap goes away. So what's needed? What's needed are systems and tool flows for current NISQ quantum computers, architectures and organizations for future ones, and algorithms to bridge the gap. And as a computer scientist, I like to make analogies back to roughly 1950 in classical computing. And so if you looked at 1950, excuse me, in classical computing, what did we have? We had technologies like vacuum tubes and relay circuits down low. In 1950, the transistor had been invented, but it was not yet used in computing. And way up high, we had Alan Turing and others who were sort of thinking about the potential for computing and computing algorithms that went way beyond what the machines of that time could build. And I see a very strong parallel to where we are today. In particular, today we have qubit implementations way down low. We have algorithms way up high that go way beyond that gap that I referred to, way beyond what these machines can do today. But there's more. If you were trying to pick a front-runner technology in 1950 for what to build your computer out of, you probably wouldn't have chosen a transistor. We weren't building computers out of transistors yet. And likewise, I think in quantum computing, while we have front-runner technologies, it's important to stay a bit broad in terms of our technology bets because we don't know what the actual winner will be. We just know what the front-runners are right now. And likewise, in both cases, there's a pretty big gap between these two. We know how we filled the gap on the classical computing side. We filled the gap with this rich field of computer science and computer engineering that goes from transistors to circuits to modular hardware blocks to architectures and so on up the stack. We don't know yet how we're going to fill that gap on the quantum side. We know a bit about what the to-do list is. You can see it here. But it isn't clear that we're going to sort of striate in the same layered approach that we've used for classical computing. And frankly, classical computing is rethinking aspects of this layered approach as well. And so from my perspective, a lot of what's interesting to me and to many people I work with is sort of how to fill that gap, how to check items off this to-do list, and what will the future architectures of quantum be? What will someone be talking about in terms of a set of abstractions similar to the classical computing one when we go forward. So let me give one example. And this example is a couple years old now. And I particularly want to note that the IBM machines that we ran it on have advanced considerably in those couple of years. And also the IBM compilers that we ran it on have advanced considerably in those couple of years. But the gist of it and the value of this style of research, I think, remains true. The idea is in some of our work, we've been looking a lot at how do you actually compile for NISQ systems. And the interesting thing about NISQ systems is they're so small that you can actually use very sort of formal mathematical optimization techniques to do constraint-based optimization to come up with fully optimized mappings onto the hardware. The second thing, though, is that optimization is crucial. With relatively few numbers of qubits, with high degrees of noise on some of the gate operations, and with limited connectivity between the qubits. All of those things mean that the way you map from the algorithm or circuit onto a particular implementation is going to deeply affect the fit, the performance, and quote unquote, the success rate of the algorithm. By a success rate, this is something that on the classical side, we don't talk about at all, but success rate would be if I run a quantum circuit 8,000 times, let's say, what fraction of those runs actually get the right answer? So for example, if you look at a very simple algorithm like Bernstein-Vazirani with 6 qubits on a 16 qubit IBM system as it was configured 2 years ago, depending on how you mapped it, whether you used the left mapping or the right mapping, you could get very different numbers of communication operations or CNOT swaps that were required. And in the process, very different success rates. Because if more swaps are required to get the qubits close to what they're interacting with, each one of those swaps is 3 CNOTs. Each one of those CNOTs has a noise and error rate associated with it. And quickly, through sort of the compounding of that error, you can get to very low success rates, 5%. Whereas doing an intelligent mapping, knowing the topology and mapping for it, as well as knowing the noise aspects of the system, which was a second step beyond this, can offer big wins, in this case, a 10x win. So once again, there's tight resource constraints, there's high gate error rates, there's low coherence time. And what we need to do is both achieve a good initial placement of qubits onto the hardware, program qubits onto the hardware qubits. We need to do sort of communication optimizations. We need to be noise aware. And increasingly, we're also looking at intelligent gate selection as well. And current approaches have been insufficient. So what we did was we set out to look at this in a way that was mindful of different hardware attributes, but portable across different hardware implementations. I can go a little bit more into the noise awareness part. And again, this is from a couple of years ago. The IBM systems have improved greatly in their noise characteristics, but these kinds of trends are still there. And I'll show in some numbers that even across a wide range of error rates, this kind of noise aware compiling can be very helpful. So what this is we went for a month to the characteristics of the machine, downloaded them and plotted them. And so across the x-axis are different days in that month. Up the y-axis is the gate error rate. And then you can see that we've done this for a few different gates in the systems that are depicted in blue and orange and green. So the first thing you can see is that there are large spatial and temporal variations in what's happening in the system. The orange gate is considerably worse than the other two, and there's big variations from day to day as well. Second thing you can see is that there's variations in qubit coherence times as well, as you can see here. And so our goal is to be able to compile both for these kinds of variations as well as for communication topology and so forth. We did that based on sort of first placing the program qubits onto hardware qubits based on operation error rates alone. Second, sort of reducing decoherence interval errors by sort of finishing within the coherence time of a qubit. And third, reducing communication. We did this for actually 3 different systems: IBM, Rigetti, and an ion trap system from the University of Maryland. And we did so through this compiler infrastructure that you see here. So in particular, I want to show that the machine attributes come in terms of daily calibration data and in terms of routing policies, gate connectivities, and so forth. So the machine attributes are over here, and they are inputs to a compiler flow that can work across very different architectures. So in terms of my statement a few slides ago about not wanting to pick a technology winner, this kind of compiler approach allows us to do that because we have used this identical compiler flow, for example, for both ion trap and superconducting machines that were made available to us. And we experimented here with both sort of formal optimization based on satisfiability modulo theory solvers or SMT solvers, as well as heuristic approaches. And right now we're at a level where the number of qubits and the number of constraints in here is small enough that you can actually use fully optimized SMT solver approaches and get really good mappings. Heuristic approaches work fairly well, and maybe the better option as we get to larger machines. Whoops, going back. So this is an example of the kind of boost in success rates that you can get with different forms of this heuristic. For example, whether it's heuristic or optimized, and whether it is noise aware or not. The gist of all of this is about a 3x improvement in measured success rate over the Qiskit compiler at the time, and up to considerably higher success rates in some cases. Across what you can see here are a wide range of small parameterized benchmarks that we use. And I'm happy to say that in the year and a half since we did this work, this has been pulled into Qiskit. So it's actually a part of how the compiler is an option that you can use when you compile for Qiskit now. In addition, a second sort of set of insights that we've done, and we've done this across a range of machines, so a couple different IBM systems, some Rigetti systems, and as I mentioned, a trapped ion system from our US University of Maryland. Whoops. And what you can see here is the degree to which a third type of optimization, so communication, yes, noise awareness, yes. A third type of optimization is about what native gates to expose to software and how that influences the success rates of the machines. So what we see is that mixture of noise awareness plus getting the right native gates exposed can offer significant improvements in success rate. Shifting gears a little bit, I'm going to give you, so that was about the value of compiler tool flows and optimization techniques that really pull together everything from algorithms down to hardware. Shifting gears a little bit, I'm going to give you two shorter examples of other types of work that we're doing that again tries to bring in the skill set of computer scientists to look at opportunities where we pull something from classical computer science and apply it in the quantum world. And here the idea is to get around the challenges that we have in quantum with the lack of QRAM, the lack of sort of appropriate quantum RAM to load and store data. And in particular, there's a set of potential algorithms that rely on sort of storing a large set of classical training data in RAM. And the goal of this work is to look for something called core sets, to look for something that is a smaller, essentially you can think about it like a basis factor, a smaller set of data, easier to store in qubits rather than in some huge QRAM, a smaller set of data that would allow the algorithm to get to the same modeling results, but with a much smaller amount of storage required. And so Aram Harrow proposed this as a theoretical possibility. And what my students and our collaborators have been doing is to look at how this might work in reality. And you can see from this the degree to which the size of the core set helps improve different algorithms, and then different means of selecting those core sets can also be useful as well. So that's example number 2. And the quick third snippet I'm going to give is not about compilers directly, but about sort of a strategy that we might wrap around compilers, which is to say, as we know, modern circuits often go well beyond what a given NISQ system can handle in terms of qubit counts, in terms of time, in terms of noise. And so the question of this third snippet of research that I'm giving it as an example is, can we cut a large circuit into smaller modules and run those smaller modules on the NISQ system and then sew them back together using classical techniques? And so you can think about this as if we just simulated the whole thing, it would scale exponentially in both memory and runtime beyond the limits of what we can simulate right now classically. If we try to run it on real NISQ systems, we go beyond their size limits. The goal of this is to be able to create cuts that do run on NISQ systems and then use techniques akin to, but distinct from classical simulation to sew those outcomes from cut circuits back together to reconstruct them. That reconstruction still scales exponentially, but if we can do it at relatively fewer cut points, and if we can do it strategically, we get the advantages of quantum from the NISQ runs, and we don't hit the full classical limits of the exponential scaling until much later. So I don't have time to, this is an hour-long talk in and of itself, but basically what we do in this work is we send a quantum circuit into, again, mixed integer linear programming, or MIP cut searcher. So again, we're using these sort of formal optimization techniques from the classical world to select cut points strategically, points where the reconstruction cost will be lowest, So then we have a set of subcircuits that we can run on quantum devices, and we get the probability distributions, or essentially the measured outcomes from those quantum devices, and we can reconstruct accordingly. The reconstruction scales exponentially, but we can also use large-scale parallel techniques to get some of the scaling under control there. We have results that show both speed advantages of this approach and also scalability advantages of this approach. What I'm showing here are the speed advantages. So if you have a NISQ machine with 10, 15, 20, or 25 qubits available, and you have these sets of algorithms sized to be beyond what can be handled by those machines, what we show here is, first of all, classical simulation is the black line that you see on each of the graphs, and then the colored lines are different options for cutting it and running it in this hybrid style. And what we can see is that for all of these, there are points where the cut can achieve considerably better times than classical simulation, despite the reconstruction cost that it faces at the end. And I don't have time to show you, but I could show you other results that show us scaling out to 100 qubits with particular focus on portions of the probability space that are of interest. So this does achieve a scaling win as well as a speed up win in different setups. So what's next? I showed this slide before. This is where classical computing landed. I would argue that based on the 3 examples I've just shown, quantum computing isn't going to striate into these hard layers of abstraction anytime soon. And in particular, if you think about the compilation example and the cutting example that I gave, both of those rely heavily on full information flow. You need to know a lot about the algorithm. You need to know a lot about the qubit implementation. And so you don't have the luxury of, in classical computing, we have the notion that an instruction set architecture is an abstraction layer that shields the software from knowing deep specifics about the hardware. The software doesn't know how much cache memory there is, how much main memory there is. The software doesn't know whether this is an in-order or out-of-order microprocessor, and so on and so forth. We've had those luxuries in the classical side because we have sufficient resources. In the quantum side, we don't have the resources yet, and we don't have the noise levels yet for those kinds of abstraction luxuries. So what I've shown are different optimization techniques that almost always need this sort of full stack vertical connection. And so as an architect from the classical space, it's interesting for me to think about how this will suss out long term. Okay, so that was me coming at this as a quantum computing and a researcher and as a computer scientist. But as I mentioned, in February, I took on this other role leading the Computer and Information Science and Engineering, or CISE, directorate at the United States National Science Foundation. And so the second half of my talk is sort of looking forward on how NSF views this space and what we are doing to catalyze research in it. And so one thing that NSF is very proud of is, so NSF was founded in the aftermath of World War II. We turned 70 years old this year. We're founded to be the United States All of Science and Basic Science Research Agency. And so for any topic, whether it's Turing Awards, Nobel Prizes, quantum, biology, whatever, you give us a topic and we can show you the fundamental research that came out of NSF funding. It's something that we're really proud of, the sort of long game that we have played on many important research problems. Here's a few. The no cloning theorem, the paper, one of the key papers on that acknowledges one of our NSF awards from 1978. Aspects of quantum squeezing for metrology, also an NSF award. Toffoli gates and quantum Fourier transforms also have roots that include NSF awards. So this is something we're very proud of. And as I mentioned, the different fields vary, but in computing and information science in particular, over 80% of the academic CS research in America is funded, the federal funding comes from NSF. So there's a very strong connection here. What NSF wants to do now is to fuse together the many research areas that contribute to quantum in order to build this sort of interdisciplinary or convergent quantum community. And so I showed you some of the examples of foundational investments in quantum going back decades. That continues. So more than 2,000 awards and 1,200 PIs supported over 40 years. That continues to this day. And in my directorate, in the CISE directorate, we have reinstated a Foundations of Emerging Technologies program, specifically to make sure there was a home within the computing space for people to explore emerging technologies, which includes a wide range. So it includes quantum, it also includes things like DNA storage and so forth. But the idea is that these sort of foundational and core investments continue. In addition, there's different goals for capacity building to sew disciplines together. So these are awards that include engineering, math, physical sciences, and computing working together on these problems. In addition, and I'll talk about this more in a later slide, there's the goal for workforce development. This is not sort of just about papers, but this is about creating a set of individuals that are trained at the undergraduate, graduate, and beyond level to be really deep in quantum. And we're also looking at K through 12 opportunities. So that's our primary school level to sort of plant the seeds. And then this sort of builds up towards very large institutes and foundries as well. So I won't have time to talk about the full range of programs, but one of the programs that we were really excited to launch and announce this summer are the Quantum Leap Challenge Institutes, or QLCIs. So these are a set of 3 centers that we're funding. I'll give the details about the centers on the next slide. The goal of this QLCI program overall was to, again, pull together the community to support large-scale projects. These are $25 million a center with cross-disciplinary challenge themes in each case to advance the frontiers of the research. The goal is to give them time to sort of identify and advance on a bold research agenda. So these are 5-year grants. These are basic research. I'll talk about other elements of what NSF does that are more aimed at commercializing that end of things, but this is about basic research to implement and think about what's next for quantum information processing. And as I mentioned, in almost all of the NSF programs that I will tell you about, the notion of workforce is a deeply important part of that. So that workforce includes the graduate students that we train in our labs. It also includes undergraduate research experiences in the broader space. So from the first solicitation, we received a wide range of proposals. And these 3 were announced as being the fully funded institutes. The announcement went out in July. So what's exciting about this is if you read the titles, it hopefully gets to the sense of breadth. And in particular at NSF, quantum is, yes, quantum computing, and you can see that in the middle one here. But in addition, at NSF, quantum is, as you know, quantum sensing, quantum communications, and so forth. And so the top one that's listed here is about the notion of multi-node heterogeneous quantum processors and building towards quantum networks. And the lower one here is about advancing in quantum sensing. And so, you know, $75 million is represented on this page in terms of investments. And from another of our sister agencies, so the National Science Foundation is one of the US's science agencies, and it's the one with the broadest mission and the most long-term mission of research. Our Department of Energy is another agency that has a science mission to it. And you may have heard about a month ago about the DOE announcement of 5 additional large centers in quantum as well. Workforce is something that's important at different layers of the quantum stack and at different parts of the sort of career pathways. One of the things that I, as a computer scientist, want to flag is that within our CISE directorate, so specific to computing, we created a program that encourages departments and schools and US universities, so these are CS departments, to hire new full-time faculty, typically early career faculty, in the areas of quantum computing or quantum communication. So the idea is that if there is someone who brings in classical expertise in programming languages or compilers or algorithms, but they want to get into the quantum space, the university can get 3 years of bridge funding to pay their salary to be able to hire them now, build up that expertise, and then hopefully sort of continue them into a more normal tenure track position long term. So this bridge funding is one of the ways that we in the computer science part of this space want to make sure that we're bringing in our sort of thoughts, our strategies, our approaches into the broader QIS space. Another example of a workforce program is a program that NSF has funded called Triplets. And the idea is to take students, faculty, students from all over the nation, faculty from all over the nation, and industry partners to come together to work on different quantum problems. So this is essentially a way for NSF to help fund internships, but internships that maintain a strong focus on research by keeping the faculty and industry in step with each other. And so we've been welcoming applications of students all over the country to this Triplets program. And last and most recent is what gets shortened to being fondly referred to as Q12. And so in America, we refer to our primary school education as K through 12, kindergarten through 12th grade. And Q12 is a play on words that speaks to the idea that if we want people to be ready for quantum when they get to college, we need to think about what they should have seen at different layers of their earlier education in order to sort of be, as some people call it, quantum natives, to be ready to speak about superposition, about the types of linear algebra that are important. And so there was a recent meeting and write-up jointly sponsored by the National Science Foundation, where I am, and the White House Office of Science and Technology Policy to produce and start to advance on a list of key concepts for quantum education. So this is my last slide, and I'm happy to take questions after that. I just wanted to give an even broader view of what NSF does. So NSF is known for funding basic science. You saw no cloning theorem, you saw Shor's algorithm, and so forth. In addition, we're increasingly trying to make sure that we fund the transitions and the bridges in other parts of the research space that will make the basic science as effective and as impactful as possible. And so these are 3 examples of that. One is that through what we call Dear Colleague Letter, a DCL, that we sent out in earlier this year in May, we offered support to any researcher that was already NSF funded who wanted to fund students to be able to access and learn more about the cloud-based NISQ systems that are available. So this was a partnership with industry. In particular, this was a partnership with Amazon Web Services, IBM, and Microsoft as 3 of the bigger quantum platform cloud providers with an idea to help researchers gain experiences with those platforms. So the supplements are additional money, both to pay for any charges associated with accessing the cloud-based platforms, but more importantly, to pay for student time to learn about them. Second, and probably super important to this forum, is a call for funding. You can see again the link that's here to encourage global collaborations in QIS. And so these are basically supplements that are offered to US researchers as part of allowing them to partner with international researchers. Often these international collaboration supplements are about travel funds. Obviously, we're not using a lot of travel funds right now in our world, but I would still encourage you to take a look at that and see if it sparks your thinking. Third, and this gets to the notion of sort of impact, bridging the gap between research and commercialization. NSF now has something called a convergence accelerator that seeks to bring ideas from the lab towards societal impact, which can be commercial or other. In this case, there's specific tracks on quantum information science And we've pulled in a cohort of researchers who are interested in working with commercial sponsors as well to move their research in that direction. And so with that, I will end my talk, and I'm happy to answer any questions. Thank you.
Thanks very much, Margaret. That was a very inspiring talk, touched on a lot of different things. So I'm looking at the Slack channel, and I can tell you that the topic which has aroused the most excitement was the mention of this cut QC that you touched on towards the end of the first half. So the question which I have asked, which is maybe better answered in text rather than verbally, is what is the archive number where I can read more about that?
That's a wonderful thing to ask. That is fairly early research. I'll go look and see if we have an early archive post. I will say that as a computer scientist, we are sometimes discouraged from posting on archive until it has been gone through its double-blind review process. And so I think in this case, we might have opted not to put it on archive until it got a little further in a double-blind review process.
Okay, well, in the absence of the paper for the moment, I will go on to the question of Alex Kissinger, who's asking, again, referring to that work, are these theoretical speedups that you showed, or is this based on running on a device?
It's a mix, but some of these are based on running on real devices. And the reconstruction costs are real. So the reconstruction costs are sort of run on real parallel systems, and we use dozens of cores to get the reconstruction done faster. And we basically parallelize as much as we can. We hit the memory limit before we hit the core limit. Right.
But I think it was written on your chart, but what was the largest circuit sizes that you were looking at, like the original circuits before you cut them?
So in the scalability studies, we went out to around, we went up into the high dozens of qubits, so 60 to 100 in the scalability studies, in order to show that we could go beyond what many people consider to be the simulation frontier. In those cases, we are doing a more directed probe of the space. So we aren't getting the full outcome of the space at the end. We're only reconstructing a part of the space. So you could imagine either that you have a decent guess of where the answer should lie, and you can reconstruct that part of the space to see if it does. Or you could imagine, things like Shor's algorithm, again, where by the end it should have concentrated the result into one part of the space, and you reconstruct that part. So when we scale beyond the simulation limit, it is through those kinds of focused space reconstructions.
Thanks. Okay. So again, still on cut QC, Benoit Vaillant asks, can you tell us a bit more about how how you recompose, try that again, how the reconstruction works when you compose together these smaller subcircuits? In particular, how do you handle the complex coefficients that you would expect to have in the wave function at the cut?
Right, so the exponential scaling comes from that. You can actually look at, so Aram Harrow has a paper with some of his students on the theory of this, and you can see the types of computations that are required for each different type of reconstruction. And what our work did was identify ways to find cut points that would require the lower cost reconstructions more often. And so we do account for the complex phase reconstruction. It is quite expensive. We've thought about actually using TensorFlow or something there to sort of accelerate the reconstruction even more. But I think Aram Harrow's paper is an excellent resource for seeing the types of computations that are needed at those reconstruction points. And then our work follows on it to say, hey, these aren't as prohibitively expensive as you thought.
Okay. Sticking on the subject of compilation techniques, I wanted to interject a question of my own here. So I think unless I missed it, everything you were describing, you kind of stopped at the gate level. But I know that you've been involved with some work with people looking below the gate level, pulse level optimizations of circuits and so on, in collaboration with the people in Chicago. And I was wondering if you saw much, well, do we think that this kind of suite of techniques is going to be something that's going to be part of the armory for a long time, or is this really just to get us through the NISC days until things get better?
So I can give that answer for the work that I talked about here, and then I can talk about the pulses after that. So I think that the suite of techniques that I talked about here and things that follow from it are going to be with us for a while. I think it's really instructive to see how much leverage one gets by knowing the connectivity of the gates, by knowing the noise parameters of the gates, and by being able to have a broader selection of gates to choose from. We've shown sort of huge leverage there, and I don't think anyone's ready to give up that leverage yet. Mm-hmm. I also think that by showing that we could use the same compiler infrastructure on 3 very different technologies, we've established a methodology that says you can get some degree of portability without giving up that kind of choice. So that's all good. When it comes to open pulse and those sort of pulse level optimizations of sort of what constitutes a gate, that work, I feel like it's really good to do that work. I'm not quite ready to say how long that kind of optimization is going to be with us. And in particular, well, the challenge there is that I think the builders of these systems really value the ability to work hard on a particular gate and optimize it at that level. Mm-hmm. And things like open pulse are basically giving people a vocabulary to talk about many more gates, not all of which the system provider can optimize to the same degree, right? And mm-hmm. So it could be the case that we as a community might decide we prefer a half a dozen or a dozen gates, well optimized, over the full vocabulary of open pulse and all the other things like it, to be able to optimize arbitrary kind of bespoke gates of our own. But I love that open pulse and things like it are available, because it lets us do the studies to see when that buys us something and when it doesn't. And I will just say in general, I remember a conversation about 2 years ago with a physicist who shall remain nameless. And I had said, I'm really enjoying and looking forward to getting these kinds of platform accesses, because I think it's helpful. And he said something like, you wouldn't be interested in these platforms. And I said, you'd be surprised what we find interesting. And I think without intending to toot my horn, but rather to sort of make a case for the field as a whole, I think when you're talking about 10x, 3x, 50x benefits, these are significant advances in quantum volume. And so to say that we should only rely on the physics seems to not acknowledge the degree to which the tool part of the space is advancing the quantum volume.
Well, you're preaching to the converted on that point. I'm going to ask one more question, a follow-up from Benoit about the CUT-QC, and then we'll switch on to to a different topic.
Can I just say, I hope that my student watches this. So the student who's involved in this is Wei Tang, and he, as with all graduate students, wavers between thinking this is really cool and having doubts about whether he should keep working on it. So I'm going to share the YouTube link with him, hopefully to motivate him.
Well, I mean, you could also share the Slack link so he can join in the conversation in Slack.
Yeah.
All right. So my last question is, what guarantee do you have that you get the right answer in the end when the circuit is too large to simulate classically in one piece?
I think we don't have a guarantee. I mean 90% of my work is about improving success rates, right? And so we don't have a guarantee. We can use multiple runs to build our confidence that we're getting the correct answer. We can use other scientific techniques to sanity check that answer. In many algorithms, there's a way to, Shor's is the sort of classical example of this, right? It's much easier to check the answer than it is to get the answer. And so there are a range of topics where once you have a sense of where the answer seems to lie, it helps the science of sort of either sanity checking that answer or using that answer to move the science to the next step. And it varies with the topic. So with ground state energy, ground state estimation as one thing, as you find lower ground states, you can use other techniques to check whether they seem valid.
Okay, thanks. So I will now switch over to a different topic completely. And Peter M is asking the provocative question, saying that AWS, Microsoft, and Google, they have very deep pockets. Do you see them leading the real progress in quantum computing compared to, say, the NSF?
So I think NSF has an $8 billion budget. That's billion with a B. And $8 billion is not a small budget. Obviously, quantum is not the only thing we fund. It's an all of science agency. So I think as any science funding agency anywhere grapples with, you have to spend the money strategically in order to cover the space well. I think there's huge value in having academic researchers, in having researchers outside these companies exploring opportunities and advancing the science, partly because we can cover the more forward-looking parts of the space that the companies aren't covering, and partly because we can do comparative and cross-platform things that the companies are unlikely to do, right? So as an academic, with my academic hat on, I was able to compare multiple commercial platforms, not to benchmark them against each other, which I think wouldn't have been scientifically appropriate, but to look as a scientist at what were the attributes of each platform that were working well. And that's the kind of research that a single company cannot do. So it's about playing our positions in the space. I make the analogy I'm totally not a player of soccer, football, whatever you want to call it, but I make the analogy that when done right, research and research funding should be like a well-played soccer game and not a soccer game amongst 5-year-olds, right? So 5-year-olds sort of chase the ball wherever it goes and they don't play positions. Hopefully in the research space, we're playing our positions about long-term versus short-term, about things that are very deployment-oriented. So, there are companies that built large systems simply to run one algorithm that wasn't actually useful, except as a demonstration point, right? So that's good. That focus on a particular kind of moonshot is good. But science agencies also have the opportunity to knit together different efforts and to go beyond where we are. And so our $8 billion gets dwarfed by what industry spends on R&D globally each year. But if we spend it well, we can keep having wins like a no cloning theorem and so forth to be able to show.
So sticking on the topic of the NSF's funding activities, so quantum computing is in quite an interesting position now, where there's like almost equal weight between the academic scientists, between the big companies and a lot of startup companies. So in terms of interactions with a funding agency like the NSF, how do you weight these different sectors? Do you treat them all equally, or how does it go?
I think we do try to keep them all equally. And one thing that slide about the quantum platforms access supplements that was just part of the previous question, one thing I should note is that 2 of those platform access points, Amazon Web Services and Microsoft, both are actually consortia of a dozen or so smaller companies, right? And so in working through those three providers, we actually made accessible something on the order of 20 or 30 different frameworks, different companies. So that's one thing to note, is even there where we were partnering with well-known names, there were smaller companies involved. When you look at the Convergence Accelerator opportunities that I mentioned on my last slide, that's an example. This is something that if you know NSF, you might consider this to be way outside the norm for NSF. So NSF is kind of the long-term science agency, the basic science agency. That's how it's known in the US. So to be looking at bridging the gap to commercialization is not part of our stereotypical personality, but it's something we're doing now. And quantum has been a really interesting opportunity here because there were people at NSF who didn't know if you could do a convergence accelerator on quantum. And then there were other people who said, oh, you can. And these small startups came in droves. So they went from wondering who would be there on the company side to having several dozen startups engaged. So that's an example where they can engage. NSF has other programs. It's sort of an alphabet soup, but there's one called IWQC20, which is specifically about industry, university research connections and collaborations. And that's another example where we fund a university that wants to explore a space and look at commercialization opportunities in that space. And then they bring in an industry consortia. And so they can reach out to companies of arbitrary size through things like that. We also fund the QLCIs and other large grants in the quantum area almost always are either required to or choose to have an industry advisory board. And you'll see the scientists, again, reaching out to this broader community. So I think the small companies in quantum have shown themselves to have a uniquely effective voice actually in this area relative to some other startup areas.
Okay, thanks. We have two more questions, which I will take, and I think we could probably wrap up at the end of that one. So the first one is from Nathan Fitzpatrick, and he's asking whether the question is about the benchmarking performance of quantum computers. So we know about the quantum volume. Nathan is asking whether you think that the gate speed should be included in these performance measures, because in real experiments, the fact that the circuit takes a certain amount of physical time to run turns out to be important.
I think it will. So speed will be important at different points for different reasons. When we did our studies, our comparative studies, getting operations done before the decoherence interval was tended not to be the limiting factor. Error rates would compound and hit you before you hit the decoherence interval per se.
So let me clarify, sorry, that should have been more clear originally. Nathan is talking about the situation where he wants to run like a variational experiment on an ion trap, for example, where the coherence time would be great, but it's going to take him days to complete the thousands of executions of the circuit that he might need to do for his experiment.
So I think we will in time care about those times, but considering that we're, for some of these things, we're talking about taking something for which we simply cannot get an answer now. And if you tell me as a scientist, you can't get the answer to this question now, but if you're willing to wait a week or 2 weeks, I'll give you the answer. Then I think people would say either one is fine by me as long as I get the answer. So I think I do see a point where the gate speeds will matter as we start to sort of bring this up towards scale and towards reality. But I think for now, that shift from intractable to tractable is such a big shift that the speeds of the gates are not on people's minds as long as the error rates are appropriate. I mean, and also if you, when we run on things like IBM, most of the time is actually in the queuing time and in the setup time and so forth. The gate speeds are negligible right now. And by the time the gate speeds would matter, most NISC systems, the compounded error would get you first. So I don't see it as an issue that's on our minds today, but maybe eventually.
Okay, thanks for the answer. And a very quick question to wrap up from Ruben Andre Barriero. And he's asking, are there plans to have a summer school in quantum science from the NSF anytime after this COVID situation is over?
So NSF tends to fund stuff rather than doing stuff ourselves. And so, for example, one of the NSF funded programs, STAQ, S-T-A-Q, from Ken Brown and other colleagues at Duke, so STAQ is a full stack ion trap computing effort, and they have run extremely successful summer schools. So the first time they offered one, they were planning on 50 people, and they ended up getting so many applications that they came back to NSF, asked for more money, and I think they scaled it up to a couple hundred. I actually, off the top of my head, can't remember whether they did it virtually this year. But clearly, well, for example, the IBM Qiskit Summer School was an extraordinary thing, right? It went from a modest plan to thousands of people signing up in essentially every time zone, and they went with it. So I think there's no reason to believe we need to wait for after COVID. I think the virtual summer schools are working, and NSF is happily funding some, and there are other ones out there too. Thanks.
Okay, thank you. So with that, I think we'll wrap up the talk. Margaret, I hope you will be able to stick around and chat to people in the Slack. I'm sure there'll be some follow-up questions happening there. Thank you for the lecture. It was wide-ranging and exciting in different directions all at once. And thank you to everyone who listened, and we'll see